Okay, last time we start and actually finish the introduction of Lyapunov function theorem. Okay, we introduced why we need a Lyapunov function to do stability analysis, and we gave the theorem. And I think we somehow prove or argue through why its condition should make sense. I strongly encourage you to go through the proof very carefully. And I think that's kind of important. At least you need to understand all the steps at least once for your entire life. Then you know exactly what's going on. Here, before I start, I would like to maybe summarize a little bit about the Lyapunov function theorem. I think maybe we can just start here. For the Lyapunov, no stability. What we actually need is that exists a function of C1 function V, such that V, this is not twist, this is V, okay, this is function of state, okay? This V is positive definite, and V dot along the state trajectory, which is defined as, if we want, it's just V dot along the system trajectory is negative semi-definite or negative definite, or negative semi-definite, all right? I emphasize, maybe Liu Ben, what do you think? Why we need this condition again? What does this condition mean? P is positive definite.
That means when the system go to the in equilibrium, the V must
Yes.
to go to zero.
Okay. This is kind of, although I use this term not in a formal way, observable type of condition. It's because, as we mentioned before, we don't want to solve the system trajectory to prove convergence. We want to use a simplified or lower dimensional scalar differential inequality equation to kind of analyze the system behavior. So we want to make sure all the bad behavior of the state trajectory will be reflected in the function behavior, V behavior, right? So that means positive definite is observable in the sense that whenever the state is not at zero, is not at the equilibrium, then the V is not zero. Okay, that's exactly the definition of positive definite. Also, so whenever V becomes zero, that means the entire trajectory converges to zero, which is the equilibrium in Rn, all right? And V dot is negative definite, negative semi-definite means that V never increase or at least decrease, and eventually, because V is all positive, right? Always positive, so eventually will converge to zero. So it's kind of scalar type of image in your mind, and because of the first condition, you somehow link with the high dimensional trajectory of evolution. So that's why roughly, let's say, what the Lyapunov function theorem, the essence of Lyapunov function stability result. Okay, I hope you can just think about these two conditions. It should make sense to you, actually picture-wise. That will be better, okay? And we gave examples last time, and to verify, okay, sometime I can try different Lyapunov function candidate to show stability. And sometimes maybe it's not easy to find a Lyapunov function, but that doesn't mean the system is unstable. Actually, it just means sometimes means we cannot, we did not work hard enough to find one. All right, so the Lyapunov function theorem is only a sufficient condition. If you can find one Lyapunov function, you can prove its convergence. But you cannot find one doesn't mean it's unstable. Okay, so that's the one of the drawback of the Lyapunov function. All right, now let's talk about a stronger condition, which is not asymptotic stability. It's the exponential Lyapunov function stability. Exponential Lyapunov function stability, or stable in the Lyapunov sense, or exponential stable in the Lyapunov sense, is somehow stated in this theorem, means you should be able to find an exponential Lyapunov function. Okay, the function condition is more stronger, or it's much stronger than the asymptotic stability condition we have before. Okay, in fact, this is more important. I would say, very important for applications. Okay, so construct an asymptotic stable Lyapunov function is often very hard. In fact, most of the practical problems I encounter in reality, I often need to find exponential Lyapunov function. All right, so this result is more important and also less involved. The proof is a little bit easier because you impose such a stronger condition. All right, so let's take a look at these two conditions. Again, you should be able to find a function or continuous differentiable function satisfy these two conditions, the first condition and the second condition. Maybe Yangxing earlier?
Yeah.
Okay, so what do you think the first condition implies? Does this imply V is positive definite or not?
Yeah, it should because it's positive.
Okay, so it's bigger or equal than something norm, right? I mean, the norm, I didn't say what norm, actually any norm works. If we take a look at this kind of maybe two norm, things like that, picture-wise is like, suppose, let's say K1, K2 is something like, this is if it is two norm squared, okay, then there will be like a quadratic function of x, right? Then V is above this thing, right? The function value. So it's definitely the positive definite. It's somehow sandwiched by two quadratic functions, all right? Maybe something like this. Okay, maybe in between, at least this function is definitely positive definite. It's not only positive definite, is bounded below by a kind of if you think about this two norm is a quadratic functions, right? So this is much stronger. I would say yes, this is a positive definite, and also it's stronger than positive definite. So this is the condition we require. And also, this is also, think about this. This is also radially unbounded. Okay, locally, like this is radially unbounded, this function value. And also, the second condition is I introduced this notation. I don't want to use that much. So this is nothing but V dot along the x trajectory. It's the derivative of V with respect to time, because x change over time by following the vector field. So V is a function of x. So V also change over time. So V dot is the derivative of V with respect to time along the system trajectory. So this condition means it's definitely so of course means V dot is negative definite. So it's definitely a asymptotic stable, but that's not enough. We not only require it to converge eventually, we also want to guarantee it converged exponentially. It's not a very slow convergence, it's an exponential convergence. How do we guarantee that? This one is okay. It's negative definite because the V dot, this part, is less than something times a positive definite function. So it's a negative definite, right? In fact, this tells us V dot is less than equal to negative K3V. If you look at V as a function of time, forget about x is the intermediate variable. If we view V as a function of time, its derivative is less than a positive number times itself. Okay, so this gives us a scalar linear differential, not equation, but inequalities. Okay, so this is a key inequality that we need to use. Okay, so let's prove this one. For example, the exponential convergence is much easier to understand and easier to prove, and also easier to construct. So let's take a further look of these two conditions. Why these two conditions can guarantee existence? Sorry, exponential stable. All right. So proof, I wouldn't call that real proof. That's a proof of sketch. The proof sketch. Okay. Let's recall the reason we introduce the Lyapunov function is we don't want to analyze high-dimensional, very complicated dynamics. We want to understand scalar order differential equations so that we can, so everything becomes easier. So recall that suppose we have a linear differential equation, first order, and the scalar. Z is R1. Let's say Z is R1. The Z dot, suppose Z dot equal to negative K3Z, Yangjing R. What do you think is the solution of ZT? This is a differential ODE. This is ODE, right? This is ODE.
Yeah.
Okay. What is the solution of ZT?
Is E 然后负 KT K3T
Okay,
Z.
K3T Z 0, right?
Yeah.
Okay. We review this even when we introduce the matrix exponential. This is the scalar case, the building block for us to understand linear differential equation. All right. So this is the fact that everyone should be able to accept. All right. Then I'm going to tell you a fact, but this fact is intuitively easy to understand, but you can look further. I don't think I want to introduce that. But comparison theorem, a comparison is really try to compare solution of differential equations based on their vector field. Okay, by comparison theorem, let's accept that as a fact. So V dot less than equal to K3V. You see, this is equality. This become inequality. Okay, but all of them are scalar case. Okay, inequality, if you view that as a time, this can tell us V as a function of t less than equal to this solution, e to the negative K3t times V of 0. Okay, this is a fact I'm going to tell you, right? And by compare with this equality part, I hope you can accept this fact. I didn't prove it for you. I don't think I'm proving anything for you. I'm stating this is a fact. This is a fact. Okay. What does this VT? So V dot, the derivative of V always less than that. So the solution always bounded above by the equality case solution. Okay, under certain assumptions, but all of the assumptions are satisfied in our case. So I hope you can accept this fact. Okay, so in this case, then you know that this VT, by our definition, is not really V depend on T directly, is really V depend on T indirectly through the state trajectory. What does this mean? It's VT, what I actually mean is V of xt, right? Because V along the x trajectory satisfies this differential equation. Okay, so if that's the case, we can conclude, let's say xt norm reach to arbitrary power. This alpha can be anything. Okay, 2, 3, 4, 5. You can think about this as 2. Okay, that's fine. Less than equal to, let's use our first condition now, right? Less than equal to, let's say xt, if you move this k to the right-hand side of this first inequality, what we have is 1 divided by k v of xt. So this inequality, these two inequality holds for arbitrary x. So no matter what state you are at, located at now, then this inequalities hold. Then I can say xt raised to the power alpha less than or equal to 1 over k1, sorry, k1 times v. And then I can use the other, sorry, I can plug in this part, right? So Vt is less than that. So this is 1 over k1. We know this guy is less than this. So this will be e to the negative k3t v of 0. This 0 is not really v of 0. V is a function of x, right? This is x at time 0, sorry. Okay, then we can use the other bound to bound to the other side. So which we can say this is less than or equal to k2 divided by k3 e to the negative k3t x0 raised to the power alpha. Okay, any questions? So overall, I will call, let me think, this overall whole thing, what did I say before? This is c e to the negative, this is some constant anyway. I will not write down formulas. So essentially, I will conclude the xt norm is bounded by some constant c, let's call that c, times e to the negative beta t x0 alpha. So the norm, let's not worry about alpha, it's fine. So the norm is decrease exponentially fast, eventually will become 0. Okay, so whenever I can find such a Lyapunov function, and I can conclude the state trajectory actually converges exponentially fast and bounded about by this this convergence, right? Here the beta will be this k3, c will be this guy. Okay, so this is exactly the requirement for exponential stability by our definition before, I think, right? Where is it? Wow. Here, right? And so that's decays exponentially fast. All right, we finished the exponential stability proof, and looking for this actually can be formulated as a optimization problem that we are going to introduce maybe in the next 2 lectures. Okay. So this is super important. I want you to be able to prove everything. Then let's move to the next topic. So we finished talking about general Lyapunov theorem for general nonlinear systems. Okay, now let's look at a particular case of linear systems. For linear systems, we actually we can solve linear system. We can find the solution or state trajectory analytically, and this allows us to establish some equivalence of different results related to stability of linear systems. Okay. So this is the important thing. That's a building block for many other tools. So I think I need to spend some time for this special case. Okay, nothing is new here. It's just special case of our previous result. Okay, let's first review a little bit about our autonomous, our linear system. If we only consider autonomous linear system, then we don't, typical linear system is AX plus BU, right? We assume somehow we don't have U, or U has been determined through a feedback law, so we have a closed loop A in that case, right? So let's consider x dot equal to AX. Okay. In this case, in our first, I think very first lecture, we talk about matrix exponential. So in this case, the solution of this linear differential equation is given by e to the at times initial state. This is the case analytical solution, right? So we know exactly how the solution relate to the A matrix and also the initial state of the system. And in this case, because we have analytical solution, we can verify stability conditions directly. We don't have to go through the Lyapunov function stuff, right? But let's see how these two approaches may converge or connect to each other. The first thing I want to say, when we talk about stability, we always talk about stability of that system about a certain equilibrium, okay, equilibrium. I don't think that statement is true, though. If I would say with so if isolated equilibrium, so if we have isolated equilibrium, then the only possible equilibrium is x equal to 0. Okay, so let me argue that. So if we want to know the possible equilibrium, then I will say the vector field need equal to 0, right? So that means ax equal to 0. Okay, so if A is non-singular, the only possible case is x equal to 0, right? That's the possible. That's even the definition of a non-singularity of A. Maybe I will ask Liu Ben then. So if this is if, the second if A is singular, what are possible equilibrium or equilibria?
They are a space.
Mm-hmm.
Yeah. The equilibrium set is the non-space of A.
Brilliant. Yes, great. So yes, that's exactly the definition. You see this, right? That's exactly the definition of null space. So the equilibrium or equilibria, or multiple equilibrium, okay? Equilibria is exactly the null space. Okay, if A is singular, the null space is only 0. If A is non-singular, the null space is non-zero. It's actually depending on the rank of A, it has certain dimensional subspace, right? So in this case, then this null space of A is the set of equilibria. Okay. So essentially, all the points in the null space of A is a possible equilibrium. Okay. So we only consider the isolated case. Assume that A is a singular, a non-singular. Okay. Otherwise, A is will be different. Okay. You need to somehow only work on the non-singular part of A. So let's say A is suppose. Okay. Suppose. We have the isolated equilibrium. In which case, so this is x star. I'll say x star equal to 0, right? This is x star equal to 0. That's the equilibrium. In this case, I want to ask when the system is stable or asymptotic stable or exponentially stable. In fact, in this case, all of these are exactly the same. Okay, global or local, they're exactly the same. As long as we assume that we only have one equilibrium. So in this case, because A is non-singular, A is squared. So A is, I don't want to prove the most general case. Let's just argue through this. Let's say for simplicity, consider a simple case. Which you can show some, you can see some flavor of the proof. Okay, simple case when A is diagonalizable. A square matrix is diagonalizable, but well, some square matrix is diagonalizable, some matrix is not diagonalizable. Okay, let's not worry about the other case. But all the square matrix is block diagonalizable into the Jordan form. But let's think about this simple case, the diagonalizable case. You can see that A equal to, let's say, T D T inverse, similarity transformation, where this D is lambda 1, lambda 2, all the way to lambda n. That's the eigenvalues of A. If that's the case, then we can say, we can see that e to the at times x0. Let's just say e to the at. By our property of matrix exponential, even the direct definition of matrix exponential, we know this is equal to t e to the d times t inverse. Okay, we show this and also use this fact several times already. This is a t. Okay, then this guy equal to, if e to the d of t, the diagonal matrix, then you can see that this is essentially e to the lambda 1t, e to the lambda 2t, all the way to e to the lambda t nt times t inverse. Okay, I'm not sure whether I showed this before, but I think this is a simple fact you can check directly from the definition of matrix exponential. Okay, so in this case, we can see these are constant matrix, does not depend on t. The only thing that affect the symptotic behavior of this e to the at is on the diagonals of this diagonal matrix, right? So because lambda can be complex number, so right, so this is, I would say, if the real part of the eigenvalue of lambda I is less than 0, strictly less than 0, then we can conclude every entry of e to the at will convert to 0. Okay, let's say for all I. So if the real part is less than 0, that means each of these elements are e to the negative number of times t. Of course, there's a complex term, but that's only cause oscillation, doesn't affect the norm. The real part of this less than 0 means all the entries will convert to 0, exponentially even, right? So in that case, every entry of the whole system, once you multiply by a constant matrix t and t inverse, we also convert to 0. Essentially, I would say, then e to the at times x0 will converge to 0, I would say exponentially. I hope you can see that this requirement. If you think about this lambda I, let's suppose lambda I equal to e to the -2 plus j times t, right? You will see that this whole thing, the norm, will eventually converge to 0 exponentially, right? So in this case, symptotic stability is equivalent to so whenever you want to exponent asymptotic stable, you have to have exponential stable, right? So it's exponential stability and the asymptotic stability are the same. I hope that's fine. So by this simple argument, although it's not a formal proof, I hope you can accept that. Let me draw this. Call this fact or theorem. So the origin x star equal to 0 is asymptotic stable and also exponentially stable. They are both the same condition, exponentially stable, if and only if the real part of all the eigenvalues is strictly less than 0. Okay, so that's a fact. That's maybe some people already know it. We don't, this is I think it's require a class to teach you entire linear system theory, but let's accept this as a fact for linear systems. But this stability is concluded directly from definition by having by using the analytical form of the state trajectory. Okay, so this kind of analysis would not be possible for other case if we don't have the analytical solution. So now let's think about what we have learned so far for Lyapunov function. Okay, so for Lyapunov function, it does not require you to solve analytically about the differential equation. It really relies on the fact that whether you can find some kind of a certificate function, which is called Lyapunov function V, such that satisfy the two Lyapunov function conditions. So let's look at it this way. Let's propose a candidate. Again, we don't know what the form of Lyapunov function could be. It could be many different forms will work, or none of them will work. But let's assume we consider a very simple quadratic function. It turns out this function is good enough. This class of function is good enough for to study linear system. But for now, let's assume that we try this quadratic function. It's almost like energy. You know, the simplest quadratic function is the norm, right? Squared. That means x transpose times I times x. That's the x norm. If you want to make a little bit more general, you parameterize. That's called the matrix induced. This kind of a norm. So that's what x transpose times p times x, where this p is positive definite. Okay. So if we propose this, the first condition will require V is PD. That means P has to be positive definite. That's the so let me write it down. So P is PD matrix. If we propose this form, then we have to, if we want to satisfy first condition, P has to be a positive definite matrix. The second condition is V along the vector field, along the system trajectory, along the state trajectory has to decrease. Let's look at this part. So the derivative of V along the state trajectory. This is just the, as we talked about before, this is the partial V partial X transpose times the vector field, which is AX in this case, right? Partial V partial X is, Liuben, do you know this? Partial V and the partial X. It's the gradient of this function. X is a vector.
Yeah. 2 px.
Okay. Yes, if you don't know this, then you kind of review the matrix calculus. So typically I review that, but this is really a graduate level class. I don't review that. You can look for online resources to see how to take derivative of this for this is the multivariate function, right? So this is P2px, that's the gradient of V with respect to x, transpose times ax, which gives us x transpose, let me think, 2 factor out, x transpose P transpose times A times X. This is the lead derivative of V along the linear vector field AX. Okay, let's call this guy A. The expression of lead derivative A. We can say, or equivalently, we can take derivative of x dot v dot, let's say xt, right? It's because it's this function, right? So if we think about the variable that depend on t is only x transpose and this x, right? We can use some kind of chain rule. We can got this is x dot transpose px plus x transpose p times x dot. This is also true. Okay. In this way, we can get, let's say, x dot is what is ax. So x dot transpose will be x transpose a, yes, times px plus x transpose p times ax. So overall, we'll have x transpose times AP, hold on, sorry, this is transpose. A transpose P plus PA X, right? So we got another expression, supposedly should be the same as A. Do you think these two are the same? Maybe ask maybe Yangxing again. So you think these two are the same or not?
I guess it's the same.
You guess it's the same. Let me first ask this question. So is two, let me write it this way, okay? X transpose 2PA, P transpose A X. Is 2P transpose A equal to A transpose P plus PA? You guess it's the same?
I'm not sure actually.
You're not sure, okay. Let's not worry about this condition. Let's directly look at this quantity, and I think that's easier to understand. Let's look at this. X transpose P transpose, sorry, X transpose P transpose A X should equal to, this is a scalar, right? Yangxing, this is fine, right? This is scalar or not? The whole thing.
Yeah, it's scalar.
It's scalar. So scalar, let's take a transpose. What do we got? It's also the same scalar, right? So A take transpose, number two take transpose is also number two, right? So take transpose, it should be equal to, again, I transpose A transpose P X. Okay, these two are the same, right?
Yeah,
they are the same. So in this way, I would say X transpose A transpose PX plus X transpose PAX, these two terms put together should be equal to 2 times X transpose, either way is fine, which I pick P transpose AX. Okay, A and B are the same, all right? A equal to B. I'm just just clarify these two ways of people proving this stuff should be equivalent. Okay. Anyway, that's some kind of remark. That's some remark. So let's typically use the fact of this. Use the B term. Okay. So in fact, this matrix is some kind of symmetrization of this 2 times PA matrix. So this matrix is actually how to say? It's a symmetric. All right. If you take transpose, these two terms plus together, it will be itself. Let me say then let's say conclude that if we want V is a Lyapunov function, if these two conditions satisfied, right? The first one is P is positive definite. P is positive definite, and what? And also the second condition is this guy is negative definite. So which we require is X transpose A transpose P. This whole thing is function as a function is negative definite. So that means this particular matrix is about negative definite. So this is A transpose P plus PA is negative definite, which is I will use that. I haven't discussed too much about the. Let me use more kind of. Let's just say P is positive definite. This guy is negative definite. We're going to introduce a lot more detail about symmetric matrix or negative and positive definite matrices, maybe just later in today's class. For now, let's say this is a symmetric matrix positive definite. This guy is negative definite. That's good enough for qualifying V as a Lyapunov function. I hope that's fine, right? So overall, I can claim, in fact, that's a fact. All right, I didn't prove that. In fact, for linear system, the quadratic form is all we need to care about. Let me say a fact. For linear system, this quadratic form of Lyapunov function is all we need to consider. It suffices, okay? If you cannot find a quadratic function which is a Lyapunov function, that means the system is unstable. In the sense that we only need to focus on quadratic functions. It could be other type of function that can show the system is stable, but the fact is that the class of quadratic functions is good enough for us to study system stability. So if we can find one, then we can find a quadratic one. If we cannot find a quadratic one, then that means we cannot find any one. All right, that's roughly the statement, the fact. I think you should be able to prove it. I mean, maybe guide you through the proof in the homework. Another fact is, so in that case, I don't think I have space. Let me zoom in a little bit. So, so in this case, so A is asymptotically stable. In this case, also exponentially stable, okay? Asymptotically stable if and only if there exists. All right, let me briefly explain that again. Hongbo asked me during break that why PA X transpose PA X also equal can be included in this term because you know that we assume that, let's say, in the proof of A equal to B, we assumed P is symmetric, okay? So in that case, P transpose A equal to PA, right? That's where this term comes from. Otherwise, we should have a transpose P here, okay? I hope that's fine. If you don't see this, I can see some confusion, but I can explain that a little bit. In fact, this 2 times P transpose A may not equal to this thing. Okay, let me give example. Let's say I have example. Let's say let's matrix. Let's say Q equal to let's say 1, 1, -1, and 1. Hongbo, is this a symmetric matrix?
No.
Okay, but can this matrix define a quadratic function? Let's say a function is X transpose QX, which will be X1, X2 transpose times 1, 1, -1, 1, X1, X2. Okay, so eventually you will see that if you, let me think, this will be X1 squared. What is it? Hongbo, can you write down the quadratic function? The first is X1 squared. The X2 term is X2 squared. And there's a X1, X2, and there's a negative X2, X1. So overall, we'll have this. Do you agree, Hongbo?
Yes, I agree.
Okay, so overall, I have this. But I can also write this as X1, X2 transpose times 1, 0, 0, 1, X1, X2. This is called a symmetrization of this matrix. They define the exactly same quadratic form, but although they are different. You see what I mean? This matrix is not symmetric. This one is symmetric. They both define the same quadratic form. Okay, I hope that's okay. So given any matrix, let's say any matrix Q, if it's non-symmetric, we can construct another matrix, which is Q maybe hat equal to half Q plus half Q transpose. That's the way to do symmetrization. Okay, they define the same symmetric, I think define the same quadratic form. I think that's essentially, I didn't want to dive into these details, but I think that's the result why these two are the same, okay? If that's make you feel more comfortable, I think I'll just talk a little bit more about this. Anyway, let's continue our discussion here from, let me restate that in here. Based on that fact, based on this fact, we know that, let's say from the fact, we implies A, so A is asymptotically stable. A is asymptotically stable if and only if, because we said the fact that all we need is to consider a quadratic function. If and only if there exists, let me say the condition here, okay? If and only if, first, there exists a P which is a positive definite, such that A transpose P plus P transpose A, but P is symmetric, okay? So when I say positive definite, I always think about this is symmetric. It's less than or equal to 0. Okay, that's what, if you assume that we want to find a quadratic Lyapunov function, that's exactly what need to be satisfied. This notation I use means less than 0, that means negative definite. This it means positive definite. Okay. A second condition that are equivalent, I will say equivalently. Well, which you may often see is another condition, which I call 2, is for any Q positive definite. Let me see. This positive definite, this matrix bigger than 0 doesn't make any sense. So I have this kind of curly type of bigger than 0 means it's positive definite. If for any Q there exists a P again, such that A transpose P plus PA equal to negative Q. Okay, Q is positive definite, negative Q will be negative definite. And so for whatever Q may be really, very much above 0, okay? It's very positive definite. So for whatever Q I gave you, you should be able to find a P satisfies this equation. Of course, whenever you satisfy this equation, that means A transpose P plus P transpose A less than 0 or negative definite. But this is another way to state the same fact. I'll call this guy. The reason I want to introduce this is because this guy is called Lyapunov function. Lyapunov equation. Lyapunov equation. You gave a Q, you solve for P. P become unknown. All right, you can solve this Lyapunov equation. I think MATLAB or other toolbox will have this thing to solve P for you. Okay. Another fact that means I didn't prove. Fact 1 is equivalent to 2. Okay, I think from 2, you can definitely implies 1, right? If you for any Q, you just choose one Q, then you find the exists P. But in fact, 1 also implies 2. So whenever you can find a P like this, then this also holds. For whatever Q, I can also find a P, but this P will be different from this existent P. Okay, so if this is the condition, you can construct for whatever given Q, you can construct P satisfies the Lyapunov equation. So maybe I think this will be homework. I don't want to prove this in class. If you don't have any clue in the homework, I hope I can give you a few steps you can follow so that you can prove these two are equivalent. Okay. Anyway, I want you to recognize A transpose P plus PA. Those thing is this kind of the Lie derivative of V along the linear vector field for a quadratic V. All right. So in summary, I think I can conclude. I don't think I prove any of them very rigorously, but at least I argue through the key things you need to know about Lyapunov stability result applied to linear system. You don't have to use the Lyapunov function to show stability of linear systems, but those terminologies are very useful for study of advanced stability result. For linear system, let's say x dot equal to ax. The system, there's only global stability. Okay, there's no local one. So let's think our equivalent system is globally asymptotically stable. The system is globally exponentially stable. These two are equivalent for linear system. So asymptotic stability means exponential stability. So you don't have a very, very slow convergence. You can if it is stable, it will converge pretty fast. These are equivalent for linear system only. Okay, for linear system. For nonlinear, exponential stability is much stronger than asymptotic stability. For linear system, these are equivalent. And as we argue through a simplified case, is that if it is asymptotic or exponentially stable, the real part of all the eigenvalues of A must be less than 0. Okay, so that eigenvalue need to be lies on the, if you study, lies on the open left half plane, right? Half plane. That's maybe in undergraduate control class, you also see these terms. This is open left half plane. The eigenvalue need to be lies open half left half plane of complex plane. Okay, the half complex plane. And also the system must have a quadratic Lyapunov function. So you can find a quadratic Lyapunov function. So what I mean by this is x transpose P of x. So if the system is stable, you can find one, satisfy the Lyapunov conditions. If you can find one, definitely the system is stable. Both we are fine. And the last one is this, for any symmetric Q, the Lyapunov condition, Lyapunov function, sorry, Lyapunov equation has a solution. Okay, there exists the positive definite P solve the Lyapunov equation. Okay, this term. When I say Lyapunov equation, I mean this equation. In this equation, Q is given, Q positive definite is given, and P is the variable to be solved. Is the variable to be solved. Any questions? I don't think we have a formal proof, but I think the key point has been really kind of argued in a intuitive or semi-heuristic way. Okay. So for linear system, it's really equivalent. Whether you can find the quadratic Lyapunov function or not implies whether the system is stable or not. For nonlinear system, we don't know what kind of class function we need to focus on. There's no general result. Okay. If you can find a Lyapunov function, it implies stability, right? So let me emphasize. So far for general nonlinear system exists. Lyapunov function implies stability, but it's only sufficient condition. If you cannot find one, doesn't mean it's unstable, all right? But in fact, there is a converse result. Actually, it's almost like a necessary condition. Let me state that. That's called converse Lyapunov function theorem. So for asymptotic stability and exponential stability, both have this theorem. In a sense, the other way also fine. So stability can also imply its existence of V, but you may not be able to find it. Okay, it's only the existence. Let me state that theorem. I don't want to prove any of this theorem, but just let you know that if the system is asymptotic stable, of course, you require the vector field to be local ellipses on the domain, and with some reasonable abstraction, there always exists a Lyapunov function and satisfy this. This is called converse Lyapunov function theory. Is this direction, right? And there always exists. It's just no way to find it. It's not constructive. This is a converse result. That is not constructive. You know the existence of such a function, but you don't know what form it follows. You don't know how to construct it, but you know if it's stable, there always exists one, but that one I don't know how to find it. Okay, you can prove those kind of existing pure theoretical result. Okay, a converse Lyapunov theorem for exponential stability means origin exponentially stable on D, C exponentially on the domain, and F is continuous differentiable. Then there always exists exponential Lyapunov function on D. Okay, we know there is one, but we don't know what particular form that function need to meet and how to find that function, because it's actually you should look for I could tell you textbooks on this. You can, if you're interested, you can find how to prove the theorems. So these proofs of the key point I want to point out is that the proofs of those converse theorems often assume the knowledge of system solution. So because typically the reason we want to use Lyapunov function is that we don't know the analytic form of the state trajectory. It's hard to construct that. So that we use some kind of simplified scalar dynamic V to infer the stability of a complicated high dimensional system. But the converse theorem, when they prove it, of course, they know there exists a solution, right? It's like existence of solution, but you cannot find a solution. They assume the construction of the function often based on the form of the solution. And we know the form of solution satisfies the asymptotic convergence result, then somehow we can use the solution to construct the Lyapunov function. So there is one. It's just like existence of a solution to ODE, but you may not be able to find it analytically. It's the same thing. All right. But at least this gives some kind of confidence. All right. If the system is stable, we should be able to find, there is a one, but whether you can find that one or not, it's art. Okay. So typically people will propose different Lyapunov function structures and to see whether it satisfies the condition or the requirement. But if it does not satisfy, you cannot conclude the system is unstable. All you can conclude is that maybe I cannot find one yet. Okay, so that's the trade-off for the surface the Lyapunov function. All right. Any questions on this part, Liu Ben?
Not yet.
No. Have you heard about converse Lyapunov function result before?
I heard about it.
Okay. What is a good converse Lyapunov function result? Is that I think well, our group also have some kind of converse result that are more useful, more constructive. Is that okay? If the system is stable, I can always find a quadratic Lyapunov function. In that case, that's a useful converse result. Okay, so okay, I only need to check quadratic functions. Then if all the quadratic functions doesn't really mean stable, doesn't satisfy the Lyapunov condition, I can conclude back the original system is unstable. Oh, that will be a little bit useful. I think my PhD dissertation talks about Swiss linear system. This always exists a piecewise quadratic Lyapunov functions. Okay, so you need to only look for piecewise quadratic Lyapunov function to certify whether the system or Swiss system is stable or not. Okay, so those are more advanced stuff. It's fun, but not that particularly useful. Let me say a few words before I conclude this lecture. So say a few words about discrete time systems, and some people may start. We'll spend another lecture or 2 or 3 or half semester to talk about discrete time system stability. But once we know the result for continuous time, I hope I somehow convey the message in spirit to you, not in the particular form. Okay, so I hope you see that all you need to satisfy, look for a Lyapunov function. Lyapunov function is almost like a certificate. It's like this certificate tells you this guy is good or bad. It's like a certificate. Okay, that certificate, if you want to certify the system is stable or prove the system is stable, you need to find such a proof, or certificate V function, which is positive definite, means that all the bad behavior of system's trajectory has to be able to show up in the system or in the Lyapunov function, right? Then you you need to show that function, its value decrease, at least non-increasing along the system trajectory. That's only 2 conditions. These 2 conditions, when I tell you, I hope I didn't say this result in a very technical, detailed way. It should be work for all dynamical system. Okay, so observable and decrease along closed trajectory. It doesn't matter whether the system is discrete or continuous time, linear or nonlinear. Okay, so those results or those kind of conditions I stated in a way that it's somehow general applicable. For example, we can conclude immediately for discrete time system with 1 slide. If you truly get the spirit of Lyapunov functions. For example, let's say I have an autonomous discrete time system. Let's also assume the origin is isolated, is also, let's say, isolated equilibrium. Okay, it's not linear. It's not linear. If the has control, you need to plug in the control law, so have an autonomous system to analyze the closed loop stability. Okay. So asymptotic stability means I can find a Lyapunov function, which is V is PD is the same. Yangxing, what does this mean again?
It's observable.
Okay. Observable, so all the bad behavior, all the let's say particular bad behavior of the X will shows up in V, right? So there should be, whenever X diverges or doesn't converge, V cannot converge. So that's this condition means. So whether it's discrete time or continuous time, that doesn't matter, right? The second one is along the closed loop trajectory, it should decrease, right? For asymptotic stability, it should decrease. Okay, so in the continuous time, we state that theorem using the Lie derivative, right? Lie derivative of V of X is defined as partial V partial X along the vector field. That's continuous time. This is a continuous case, continuous time case. In discrete time, this is the instantaneous velocity, right? Instantaneous velocity is negative of V. So in discrete time, we only have this time step and then next time step. So in this way, what we mean along closed loop trajectory is that whenever, no matter where you are, the state, the next state, the V value should decrease. Okay, that's exactly what this one says. I call it the delta F along this non-vector field. This is the state updating function. So this means along the closed loop trajectory xk plus 1, always less minus xk is this one is just the next time step x. You evaluate v at the next time step x should be less than actually v of the current time step x. So that's where this guy need to be negative definite. I'm not sure whether you can get that. It's exactly the same kind of spirit, same kind of a principle applied to the discrete time case. So this condition should work for all. This negative definite means this is important, okay? Delta f v of x is negative definite. That means it's if you state the condition for negative definite, this guy, this is a scalar, okay? This guy is less than 0 for all x belong to Rn minus the 0. Okay, if it's 0 is fine, right? Negative definite. 0 is 0. If it's not 0, any particular state value, the delta f, if you add partner state, the next time step, your v of the v value definitely should decrease. Okay, that will guarantee the asymptotic stability. If we want exponentially stable, then still, I think I asked Yangxing before this, some requirement of this v function. This definitely implies part definite, but not only that, somehow this sandwiched by two quadratic functions. And then the decrease is not only negative definite, the decrease somehow satisfies the exponential convergence type of inequality. All right, these conditions are the same as before. It's just we replace the derivative of v becomes the discrete delta of v along the closed loop trajectory. Fuzhen, is this okay to you?
Yes.
Okay. So I have a lot of dot. Okay, so there's a lot of conditions. Whatever continuous time, you can extend to discrete time. So proving discrete time for continuous case, extend the continuous time case to discrete time case is not that hard. It shouldn't be a new contribution as long as the spirit or the principle is stated clean or clear for the continuous case. All right. So that's perhaps all I want to say about Lyapunov, basic Lyapunov stability. We have learned different notions of stable stability in Lyapunov sense, asymptotic stability, global exponential or global asymptotic stability. And we also introduced the Lyapunov function, Lyapunov stability conditions. The key requirements are two, observability and also the function decrease along the closed loop trajectory. And we have some fancy math term or math notation to state that condition. The idea is simple, but you need to state that idea using math, where we have the lead derivative stuff, also the delta stuff for discrete time. Okay, for a linear system, I want you to know that asymptotic stability is equivalent to exponential stability and equivalent to existence of quadratic Lyapunov function, which you can find by solving a Lyapunov equation. Okay. I love this stuff. So whenever you have questions, we can discuss. All right. So next lecture, I will see how to construct Lyapunov function. This is only analysis so far. Now we need to talk about computation, how to find Lyapunov function using optimization. But before that, I don't think this next lecture. Okay, I think will be a lecture after I introduce the basic optimization. Okay, so we will continue to discuss stability and how to find Lyapunov function through softwares. But that will be after my next lecture, which is lecture 11.